Thanks, Ashley. My name is John Lyssand, and I'm a field application scientist with Lycor Biosciences. I cover the New York City metro area as well as Connecticut and New Jersey. Prior to joining Lycor, I was a postdoctoral fellow at the New York University. I obtained a doctorate in pharmacology at the University of Washington in Seattle, Washington. During my doctoral work at the University of Washington, I did extensive work with the Incubation assay and using this assay to study signal transduction activation following additions of ligands or inhibitors to G protein-coupled receptors.
Thank you, John. Also joining us as panelists are Vince Bovia, Senior Molecular Biologist, and Joy Kovar, Senior Scientist at Lycor. Vince and Joy will be answering the questions John is unable to address as we move through the presentation today. Panel, please introduce yourself.
Hi, this is Vince. I'm a Senior Molecular Biologist.
Joy Kovar, Senior Scientist.
Thanks, guys. All right, let's turn the floor over to John.
Thanks, Ashley. So today I want to focus on the Incubation protocol. I'll begin by giving a brief overview of the Incubation assay, but then I'll focus the majority of the time over the different steps in the protocol and highlight the areas that you need to focus on in the lab when developing this protocol. So let's begin with a brief overview. The Incubation assay starts by plating your cells in a microtiter plate. These plates can range from 6-well to 1536-well plates. Once you've seated your cells, you allow them to grow to the desired confluency. You add your treatment, whether it be a ligand, an inhibitor, siRNA. Once you're done with your treatment, you remove media, fix, permeabilize your cells, and then you add your primary and secondary antibodies directed against your target of interest. These secondary antibodies are unique in that they're coupled to an IR dye that allow for detection on either an Odyssey CLX, an Odyssey Classic, or an Odyssey SA. The Incubation assay offers a number of benefits over a traditional Western blot. Since these are microtiter plates, you don't have to use a lot of reagents when performing the assay. Depending on the number of wells in your plate, you can collect data very rapidly. And because the Incubation assay doesn't have a lot of protocol steps, you can enhance accuracy and reproducibility from plate to plate and experiment to experiment. Now, there are a number of applications you can use the Incubation for. I've listed here some, and I don't have time today to go through each of these in full. I encourage you, if you want more information on the different applications, to visit lycor.com/ICW, and on our website we have a ton of information about each of these applications as well as examples in research. So let's begin by talking about the Incubation protocol. I've listed here the different steps I'm going to focus on, including seeding our cells, treating our cells, fixation, permeabilization, applying primary, secondary antibody, scanning them on an Odyssey system, and then finally the analysis. I'm going to spend about the next 40 minutes going through each of these steps. Now, if you want help in this optimization process, I highly encourage you to contact Lycor Custom Services. If you go to lycor.com/custom services and enter your contact information, a Lycor scientist will get in contact with you. Potentially, you can send in your cells and your primary antibody, and a Lycor scientist will go through each of these steps and do all of the optimization for you. So, before we begin with this protocol development, why don't we stop and take a poll? Ashley?
That sounds great, John. Our first poll question is a true or false question. When optimizing my Incubation protocol, I should always choose conditions that have the strongest signal on an Odyssey. To answer this question, click the radio button next to your answer choice. We will give everyone a moment to choose a response. All right, it looks like most everyone has had a chance to answer. Let's close this poll. John, take a look at the responses.
So I see a lot of good answers. And this question can be a little tricky because when we optimize an INSO-Western plate, we want to choose a condition that gives us a strong signal. But just because a condition gives us a strong or a bright signal doesn't necessarily mean it's the best condition. Because in addition to signal strength, we also want to monitor reproducibility from well to well and experiment to experiment. So before we start talking about the protocol development, why don't we first address how do we determine what is an optimal condition? So when determining these optimal conditions, I would suggest to use a z-factor measurement. A z-factor measurement will compare both positive and negative controlled data sets. For example, a positive controlled data set can include your cell line of interest with a ligand of interest. Your negative controlled data set can include cells that were untreated or a basal state. Now the z-factor measurement will compare both the means and the standard deviations for both these two data sets. The more replicates or the larger number of replicates you have, the more accurate your z-factor measurement will be. So shown here is a schematic of how the z-factor measurement works. On the y-axis we have our signal, and on the x-axis we have sample number or replicate number. The data set on top is our positive control data set, and the data set on bottom is our negative control data set. The solid black line running through each is the mean for the data set, and the dotted line is the standard deviation for each. Now the z-factor measurement will take into account both the means and the standard deviations for both these two data sets. The equation for our z-factor measurement is shown on bottom, and the z-factor measurement will be a reflection of the separation between these two data sets. Z-factor measurements will typically have a score between 1 and 0. A z-factor score of 1 is an ideal score. Scores ranging between 0.5 and 1 are excellent scores and a reflection of ideal conditions for your INSO-Western assay. Scores ranging between 0 and 0.5 are marginal scores and should be further optimized to improve your z-factor score. Any score that's 0 or less than 0 is a poor score and is reflective of the fact that you have poor separation between your positive control and negative control data sets. Now, rather than having to use the z-factor score measurement yourselves, you can easily use the INSO-Western Analysis ribbon key, and by using the software that's associated with your Odyssey imager, you can easily highlight which wells are your positive control, shown in pink, which wells are your negative control, shown in cyan, and which wells are your background, shown in black. Once you've defined these wells, either Odyssey software or Image Studio software will do the z-factor score analysis for you. So let's look at an example of how you can utilize the z-factor measurement when optimizing your INSO-Western assay condition. Shown here are 4 graphs. Y-axes for each graph are signal intensity, and x-axes are replicate number or well number. Data sets shown in blue are positive control data sets, and data sets shown in green are negative control data sets. So the 2 graphs on top are comparing 2 different primary antibodies specific for phospho-ERK. We can see that both primary antibodies have good separation between a positive and negative control signal. In fact, antibody number 1 on left has a much stronger signal intensity when compared to candidate number 2. Now when we look at the z-factor scores for each of these primary antibodies, we can see that candidate number 2 has a much higher z-factor score than candidate number 1. This is in contrast to the fact that candidate number 1 has a stronger signal intensity than compared to candidate number 2. The reason candidate number 2 has a higher z-factor score is because we have good separation between positive and negative controlled data, as well as high reproducibility. So this is an example of where just because a condition or an antibody gives a strong signal intensity doesn't necessarily mean it's the best choice for our protocol. The 2 graphs on bottom are comparing different permeabilization reagents used in an INSO-Western assay. On left, we're using a detergent to permeabilize our cells. On right, we're using methanol. We can clearly see that the detergent used in this example gives a poor Z-factor score, whereas methanol gives a high Z-factor score. Because of this, when we compare these two conditions, we would want to use methanol over a detergent. So let's begin by talking about the protocol. And let's begin with the first step, which is seeding our cells. Now, before we actually seed our cells, we need to choose a plate. Now, plates come in a lot of different types, well numbers. The one requirement for these plates is their clear bottom. That's because when we place these plates on an Odyssey system, the lasers must penetrate through the bottom of the plate. So with that in mind, we need to ensure these plates have clear bottoms. Now, typically plates will come as either flat-bottomed or curved bottom plates. Now, if you're using adherent plates, you want to ensure you have flat, clear bottom plates. If you're using suspension cells, you'll want to use curved, clear bottom plates. Now, plates also come in a number of coatings. These can range from poly-D-lysine to collagen to a number of factors. If your cell line of interest comes off easily during incubations, wash steps, you might want to include a plate coating to allow for a tighter adhesion between plate and cells. Depending on your cell line, you may want to use poly-D-lysine or collagen. It really just depends on your cell line and what it reacts best with. Now, a third consideration is what type of wall plastic do we want to use with our plates? Typically, you'll see plates that have black walls, clear walls, or white walls. Shown here are 3 images. The first 2 are from black and clear walled plates containing in-cell western cells. The third image is from a white-walled clear bottom plate with no cells. Now, if we focus first on a white-walled plate, we can see that even though this plate does not contain any cells, the white plastic is causing high background within the well when scanned on an Odyssey system. Because of this, you need to avoid white-walled plates. Now, both black and clear-walled plates work well for an in-cell western assay, but of the 2, black-walled clear-bottom plates will offer better background than a clear-bottom, clear-walled plate. So once you've chosen a plate, we're ready to seed our cells. The number of cells you seed will range between 15,000 and 40,000 cells per well. The time allowed for incubation will range between 2 and 3 days. Now, both these values will vary greatly from cell line to cell line. Now, the number of cells you decide to seed and the number of days you allow to incubate should both result in a final confluency level of 70%. Shown here is an example image of a plate with less than 10% confluency and a plate ranging around 50 to 60% confluency. So choose a cell density and an incubation time that allows you to reach the 70% confluency level. Suspension cells are a little different. Suspension cells have a characteristic that when they're placed in serum-free media, they'll form a monolayer on the bottom of the container. Once that monolayer is formed, the remaining cells will remain in suspension. So for suspension cells, what you'll do is place your cells in a flask in serum-free media. Allow that flask to incubate for 30 minutes to allow formation of that monolayer. After 30 minutes, count the remaining cells in suspension and then seed your microtiter plates. Once seeded, allow incubation of those plates for about 10 minutes so that a new monolayer will form. Once this new monolayer is formed, you can then move on to your incubation and perform your assay. Now, in addition to this, suspension cells require a number of centrifugation steps throughout the remainder of the protocol. If you're using suspension cells in the lab, I highly encourage you to contact Lycor and we could forward you along a protocol that details all of these additional steps. So to summarize, for seeding our cells, we take our microtiter plate with a clear bottom and we seed our cells. We allow those cells to incubate until they reach a desired confluency level of 70%. So now we're ready to treat our cells. Now, very frequently with cells, the The first question you'll ask is, do I need to serum starve my cells? Typically, groups will serum starve their cells because serum contains a lot of different components that may be activating downstream signaling pathways. Serum can also affect growth phases and growth rates of your cells. So whether or not you need to serum starve will be dependent upon the system you're studying. Now, before we treat our cells, we also need to come up with an experimental design. This will include questions such as, how long should I incubate my cells for? What type of controls I should include? And how am I going to normalize from well to well within a plate? Lycor offers a microplate setup guide. I've listed the website to download this guide on bottom. This is a very helpful guide when designing your experiment to easily separate which reagents you're going to use, which primary antibodies you're going to use, and which secondaries you're going to use. Feel free to download this and see if it's a helpful tool for you in the lab. So the first question during our experimental design will be incubation time. Shown here are 4 graphs. Each of these graphs will be plotting phospho-ERK over total ERK. On the x-axis is time. The top 2 graphs are looking at PDGF treatment. The bottom 2 graphs looking at EGF treatment. Now, depending on the system you're studying and the ligand you're studying, we can easily see from these 4 graphs that levels of phosphorylation change greatly over time. So when we're choosing a time period for our dose response curve or whatever treatment we're doing, we want to ensure that we choose a time point that has high levels of signal. So for this case, when we look at phospho-ERK, we want to choose a time point that has high levels of phosphorylation versus low levels of phosphorylation. In addition to time, we also want to determine which controls should we include in our plate. These include both positive and negative control cells. Negative controls can include secondary only, perhaps untreated cells, whereas positive control can include a maximum concentration of ligand, ligand alone if you're doing an inhibition curve, or even potentially untreated cells if you're doing siRNA treatments. Normalization will also be important when designing our experiment. This is because cell numbers can greatly differ from well to well. Typically, you might see groups normalizing to total protein or housekeeping proteins. Both of these 2 options require the use of a primary and secondary antibody specific against your target. Now, since you're utilizing antibodies for these 2 methods, you'll need to optimize each of these antibody conditions for your given target. A third option groups are using are non-specific cell stains, such as Lycor's CellTag 700 stain. These stains don't utilize antibody conditions and minimize the number of steps required when optimizing your in-cell Western plates. In my previous webinar, I focus on each of these 3 topics and compare them to one another. I highly encourage you to watch my previous webinar if you want more information about the benefits and downfalls to each of these methods. To summarize, once our cells have reached a desired confluency level, we remove media, serum starve, add our ligand of interest, incubate for a desired period of time, remove our media, and now we're ready to move on to the next step. So the next step in our protocol is fixation and permealization of our cells. The goal of fixation is to capture our cells in a near lifelike state. Typically, with fixing agents, you'll see 2 categories. They'll exist as either denaturing agents, such as alcohols and acetone, or cross-linking agents, such as formaldehyde. The denaturing agents include reagents such as methanol and ethanol. The mechanism of action behind these reagents is that they disrupt hydrophilic bonds and allow release of hydrophobic bonds. Because of this, proteins irreversibly fall out of solution. Now, this will disrupt your cell and disrupt the cell membrane. Because of this, no additional reagents are required for permealization. Cross-linking agents, on the other hand, form cross-linked bridges between molecules within the cell. Formaldehyde specifically forms cross-linked bridges between proteins, nucleic acids, and lipids. And a working solution of formaldehyde should be roughly 4% weight per volume. Paraformaldehyde is a polymer of formaldehyde and is also frequently used in in-cell westerns. Now, because these agents only form cross-linked bridges, the cell membrane will still be intact. Because of this, we'll need to use a detergent to permealize the membrane to allow our primary and secondary antibodies to enter the cell. So here's an example of how a Z-factor score can be used to compare different fixation and permealization conditions. Shown here are 3 plates. In blue is using Triton X100, and in red, methanol. By comparing these two conditions, we can easily see that methanol is a superior fixation and permealization reagent compared to Triton X100. So for this given condition, we would want to choose methanol because it gives a better Z-factor score. Now, there are a lot of different options out there for both fixation and permealization of your cells. And for most cases, all can work. I've listed some examples here, and I highly encourage you to go to Lycor.com to obtain protocols in how to optimize the fixation and permealization conditions if neither methanol or formaldehyde or paraformaldehyde work for you. So to summarize, once we're done with our treatment, we fix our cells with a reagent such as formaldehyde, we incubate, remove our fixing agent, we permealize with a detergent such as Triton X100, we incubate, remove our detergent, and now we're ready to move on to the next step. So now we're ready to apply our primary and secondary antibodies. But first we need to select a primary antibody. Just because a primary antibody has worked well for a traditional Western blot does not mean it's going to work well with an in-cell Western. Shown here is a schematic of a protein in its fixed native state, as well as that same protein in its denatured state for a traditional Western blot. Now, some primary antibodies will work great for both applications. The primary antibody can easily bind to its antigen binding site on both a fixed native state protein as well as the denatured state protein. Some primary antibodies can only recognize a discontinuous antigen binding site, meaning it can only recognize an epitope in a fixed native state and not a denatured state. Thirdly, some primary antibodies can recognize denatured state antigen binding sites, but that same antigen binding site might be masked or hidden in a fixed native state protein. So when you're selecting your primary antibody, it's important to look at the data sheet. When you're looking at the data sheet, you want to check and see if it's been validated for either immunofluorescence or immunocytochemistry. If it's been validated for either of these two applications, that implies that it's been validated for fixed native state conditions. Additionally, if a primary antibody has been affinity purified, that will also ensure high specificity. If you have to choose between polyclonal and monoclonal antibodies will give a much purer form of your antibody directed against your target of interest. Now, once we've chosen a primary antibody, we need to validate it by Western blot. Now, when we run this Western blot, we want to make sure we're going to use the same cells as we'll use in our in-cell Western. We'll want to compare both positive and negative controls, and we'll want to use mild lysis conditions, avoiding SDS as much as possible. Now, once you've run your Western and you've imaged it on an Odyssey system, there's two things you want to look for. First, you want to confirm that your target of interest is at the right size. Secondly, you need to ensure there are no non-specific bands. If there are any non-specific bands on your Western, that is non-specific noise that can compete with your target of interest in an in-cell Western format. So if you have non-specific bands, you'll need to further optimize your Western conditions. You can optimize these conditions by changing your blocking buffer or potentially choosing a new primary antibody. At Lycor, we offer primary antibody support. If you go to lycor.com/antibody request and let us know what your target of interest and application of interest is, in this case in-cell Western, we will curate published data and forward along to you any references that have examined your target of interest in an in-cell Western format. So what this means for you is that we can potentially help you find primary antibodies in published data that have already been looking at your target of interest. Now, once we have a primary antibody that's been validated by Western blot, we can then move along into the in-cell Western format. Once we move to the plate-based assay, we'll want to make sure we optimize antibody concentrations, again by comparing both positive and negative controls. Perhaps we'll want to look at dose response curves and inhibition curves to ensure the system is responding as it normally should. Additional controls, we can pre-absorb our primary antibody with antigen to ensure that it's binding to the target of interest. We can also examine these cells under a fluorescent microscope to ensure the subcellular localization of our target of interest is located where it normally should. Now, in addition to our primary antibody, we also need to select an appropriate secondary antibody. Secondary antibodies come in a lot of different forms. Very commonly, you'll see some secondary antibodies that are highly cross-absorbed, and some secondary antibodies that have no cross-absorption. What cross-absorption does is it takes a secondary antibody, such as a goat anti-rabbit, and it ensures that it won't non-specifically bind to mouse, human, rat primary antibodies. So in the figure shown, the secondary antibody on left has not been highly cross-absorbed. We can clearly see that our goat anti-rabbit secondary, in addition to binding our rabbit target, is also non-specifically binding to our mouse primary. Once our secondary antibody is highly cross-absorbed, as shown on right, that non-specificity disappears. At Lycor, we only offer our secondary antibodies as highly cross-absorbed to eliminate any guesswork when selecting a secondary antibody. Lycor offers a number of secondary antibodies with a number of fluorophores. Very commonly, you'll see IRDI 680RD, IRDI 680LT, and IRDI 800CW. Of these three secondary antibodies, you will not want to use the IRDI 680LT. The IRDI 680LT will cause high background in plate-based assays. So of these three secondary antibodies, the IRDI 680RD and the IRDI 800CW have been optimized for the INSO Western assay on your Odyssey system. So to summarize, once we've fixed and permealized our cells, we'll go ahead and block using a blocking buffer such as Odyssey blocking buffer, add primary, add secondary, and again, these secondary antibodies will be unique in that they're coupled to either IRDI 680RD or IRDI 800CW. Now, once we've applied our secondary antibody, we're ready to scan our plates on an Odyssey system. If you're utilizing an Odyssey SA, the Odyssey SA is designed to hold your microtiter plate in a fixed position. If you're using either an Odyssey CLX or, as shown here, an Odyssey Classic, you have a very large imaging surface to place your plate. When using either of these systems to read your INSO Western plate, it's important to utilize the L bracket that came with your Odyssey system. This L bracket will create a right angle in the lower left corner. This L bracket will make it very easy when you open either Odyssey software or Image Studio software to place a grid around your plate of interest and allow for the plate to sit at a fixed right angle to the Odyssey system. Now, shown here is Image Studio software in the acquisition ribbon with all of the different settings you can utilize when scanning your plates. I don't want to go through each of these different settings for the purpose of today, but I'll just simply focus on the settings that are important for your INSO Western plates. Before I do, why don't we stop and take a poll? Ashley?
All right, everyone, our second question is another true and false. Take your best shot at answering. Do all INSO Western plates have the same focus offset value? Once everyone has had a chance to answer, we will close the poll. Okay, John, take a look at the responses.
So I see a lot of good answers. The correct answer, though, is false. And this is because the focus offset will greatly vary from plate to plate and manufacturer to manufacturer. So this brings me to my main point when scanning your INSO Western plates on an Odyssey system. The main setting you want to focus on when going through all the different parameters for your scan is the focus offset. Now, there are a couple different ways to determine what the optimal focus offset value should be. Very often, a plate manufacturer will report in an information or specification sheet what the distance from the bottom of the well to the bottom of the plate is in millimeters. So this would be a good starting point when determining your focus offset value. In addition to this, it's a good idea to take your plate and empirically determine what the focus offset value should be. This involves taking an INSO Western plate and scanning it at a number of focus offset values. Shown here is an example of such an experiment in which we took an INSO Western plate and scanned it at 2.25 millimeters through 4 millimeters in 0.25 millimeter increments. Shown are all the images of each scan as well as the quantitative data from each scan. What we can easily see is if we choose a setting that's too low, we won't be able to get any signal from our INSO Western plate. Alternatively, if we go too high, that will also affect signal strength. So for this given plate, when we compare all the focus offset values, we can clearly see that 3.25 millimeters is the optimal choice to choose for this plate. So now that we've scanned our plate at the appropriate focus offset, we're ready to analyze our images. Now, I'm not going to focus too much on the analysis ribbon within Image Studio today. If you want additional information about how to use the INSO Western analysis ribbon in Image Studio software, I highly encourage you to go to lycor.com/imagestudio, and in the subsequent support page, you will find a detailed webinar going in depth into this analysis. Just to focus on a few highlights in the INSO Western analysis ribbon, in Image Studio software or Odyssey software, you can easily apply grids on top of your image. You can adjust the number of wells, the shapes of the wells, whether they be circle, square weld. You can easily choose which channel you're normalizing to, whether that be the 700 or 800 channel. You can also define wells. These definitions include which are your background, shown in black, which wells are your 100% standard or positive control, shown in blue, or which wells are your samples, your experimental conditions or unknowns, shown in green. Using either Odyssey or Image Studio software, we can easily view either laser channel separately or overlaid. Shown here in red is phosphorylation of ERK, and in green, total ERK. For this particular plate, our first column is our secondary or background control. Our second column is our basal state or no ligand control. And then as we move from left to right, we have increasing concentrations of EGF, which will activate our signaling pathway causing phosphorylation of ERK. Again, using either Odyssey or Image Studio software, we can easily apply these grids on top of these images, export the data to the graphing program of our choice, and plot our data and monitor changes in phosphorylation. So to summarize, the INSO Western protocol involves plating our cells, allowing those cells to incubate, treating our cells with either inhibitor, a ligand, potentially siRNA, fixing permeabilization, antibody incubations, and finally detection and analysis on an Odyssey system. When comparing each of these different protocol steps, it's essential to use the Z-factor measurement to determine which condition is optimal over another. Again, if you want help in this optimization process, please visit lycor.com/custom services, and you could potentially send your cells and your primary antibody to our custom services program, and we'll develop the protocol for you. So this time I think we have just a few moments to take a couple questions. Ashley?
Sure, John. Our first question is, do I need to re-optimize my fixation and or permeabilization conditions for primary that already works with IHC?
That's a great question. If you've already gone through the work and determined which conditions work best for immunohistochemistry or immunocytochemistry experiments, you can use those as a great starting point for the INSO Western assay. In many cases, those conditions will also work well with the INSO Western, but I still think it's a good idea to try just a couple other conditions just to ensure you are obtaining the highest Z-factor measurement with these conditions. Ashley, do we have time for one more question?
Yes, this question is about plate storage. The audience member wants to know if she can store her plate after the secondary steps without scanning.
It's a great question. Very often you may not have time to scan a plate in a given day. These plates can be stored. The first thing you'll want to do is to each well add a little bit of blocking buffer just to keep everything wet. And then you'll want to seal the tops of the plates with parafilm or another method that will allow evaporation. Once you've sealed the plates, go ahead and store them in 4 degrees, and the plates should be good for a couple weeks. If you're looking at phosphorylation, just be aware that phosphorylation will decrease over time, and you'll want to read that plate as soon as possible. Well, great. I think that was the last question we had time for. Thanks everyone for attending the webinar today, and please contact us if you have any questions or need any help as you develop the INSO Western protocol in your lab. Thanks.
Thank you, John, and thanks to all of you for taking the time to participate in our webinar today. We will be sending information on how to access a recording of this session very soon. Please watch your email or lycor.com/webinars for details on how to watch the replay. Our panelists are still answering questions, so please stick around if you have a question that has not been answered. Or feel free to give us your contact information if you'd rather receive an email response. We will be taking questions for a little while longer, so you may still submit any questions you have. Lastly, please let us know how we can improve our webinars by answering the post-event survey questions when you exit this webinar. Thank you for joining us today, and we hope to see you at our next session.